make differentiations. That's why we deal about in the introduction of, or the introducing part of logarithmic function or natural log, which is ln. Remember last time I said that when we're given a function like this, where it's y equals to a complex function, we're supposed to introduce ln both sides for us to simplify that function. So in this case, first we're going to look at the function that we're given. It's either the function has a division, the function is multiplied, the function has a root, the function has an exponent. So if we come across such a case and the function is complex, so for us to simplify such a case, we must introduce ln both sides. If we look at the first example, they say we should find dy over dx if y is equal to the cubic root of cos 2x over x to the 4 tan 3x. Then what we're going to do first, we're going to introduce the ln both sides. Then what I can do for me to better explain this, I can just write this question here and then explain it step by step. So the question that we're given there, it's like this. It's a cubic root of, I think it's cos 2x over x4. This is cos 2x, this is tan 3x. So when we look at the question that we're given, it's a bit complex. So the simplest way to solve this is we are going to do this. So the question, remember, it says we should find dy over dx if we have the first question. So what I'm going to do first, I'm going to introduce ln on both sides, given that this question is complex. It has a division, exponent, or the functions that are multiplied, so that I can apply the logarithmic properties. So we are given this, we introduce ln both sides. Then if we come back to the logarithmic properties, we can just discuss them here. We can say log properties. Remember, when we look at the properties, we have properties like when we say log, let's say this is log b, or instead of log b, let me just say log e. Remember, log e is the same as ln, right? So this will just be log e ab. So this will be log e a plus log ab. So it's the same thing when I come here and say this is ln of ab, which is equal to ln of a plus ln of b. So the second one that we mostly look at also is log a over b, which is equal to log a minus log a b, which this last time I said that is the same thing as ln of a over b, which will be equal to ln of a minus ln of b. So once we understand these properties, it will be simple for us to apply them whenever we're dealing with any logarithmic problem. So when we check here, the third one which we can focus on now is log of a. Then we have a to the m. We can be allowed to drop the m, so we have log e a. We say right. So again, if we have things like a log or a property like this, log, let me say it's 1 over a, this will be minus log e a. Because what we did here, we just applied the same property as this. We just changed that 1 over a to this, then we drop the negative. You see, right? We're allowed to do that. Or we just apply this property. We say log of 1 minus log of a, and log of 1, we know here that log of 1 is equals to 0. Or in other words, ln of 1 is equals to 0. That we know of. So another thing, ln of e will be equals to 1. So if we know this, we'll be good to go. So now let's go back to this problem and see what we can do. Now on this problem, we can apply, first thing that we see is division. That is the most proficient one here. So we can just say ln of cubic root of, let me put it like this. I'm also allowed to put it like this, which here is 2x to the 1 over 3 minus, since it's a division there, I'm gonna say minus. Alright, so let me close here. Then I'm going to say minus ln of x to the 4 tan 3x. Then if we check this, applying the ln this side, we can drop the 1 over 3 according to this property. We can drop the exponent. We drop the 1 over 3, we have ln of cos 2x minus, this one becomes inside ln of x to the 4 plus ln of tan 3x. Right, then I can just simplify that further. Cos 2x minus, then here I drop the 4 because we're having the exponent inside the ln. So I can just drop the 4. We have ln of x minus ln of tan 3x. We see, right? Now, since we have this, we can now introduce the derivative both sides. We introduce d over dx. Then we start deriving. Now, if I try to introduce d over dx both sides, I'm going to get, let's see what we're going to get if we introduce these both sides. Let's see, this is going to be ln of tan 3x. Then when I drive ln of y, we're going to get, remember when you drive ln of something, you're going to get 1 over that something times the derivative of the inside. And the derivative of y will give us dy over dx. And this will be equal to, when I drive this, I'm going to keep the 1 over 3 first as a constant. Then ln of cos 2x will be 1 over cos 2x times the derivative of the inside, which in this case the inside is cos 2x. Right? And then minus, when I drive this, I'm just going to keep 4 as a constant. Since it's ln x, remember when I drive ln of something, I get 1 over that something times the derivative of the inside. In this case, the inside of this function is x. Then I drive the last one. This is ln of tan 3x, which I'll get 1 over tan 3x times the derivative of the inside. In this case, the inside is tan 3x. So, in this case, this will be 1 over 3 cos 2x times, when I drive cos 2x, here I'm going to get, first thing when we drive cos, we get negative sign. So this will just be negative sine 2x, then times the derivative of 2x, which 2x is the inside of cos sec function. So this will be minus, when I drive this, I'm going to get 4 times 1 over x, which this will just be 1, so I don't have to write that, plus this will be 1 over tan 3x times the derivative of tan, we know that it's sec squared, but here the angle is 3x, so I'm also going to multiply by the derivative of the angle, which is 3x. And then this will be minus 2 sine 2x, because the derivative of 2x is 2. Then I multiply by negative sine 2x, then I put it on top here, then I divide by 3 cos 2x, and then this will be minus 4 over x plus, and then this will be the derivative of 3x is 3, so take 3 times sec squared 3x, put it there, and it will be in this format, and then I divide by tan 3x. Now when we look at the left hand side, remember here we had 1 over y times dy over dx, right? And then here we can just have dy over dx, then we multiply both sides by y, and then that y will come here. You said it. And remember, what is y? We know from the beginning that y is this, so I can just easily copy this y and paste it there. So I can just easily paste the y here. So it's times this function. Then this will be our derivative. So not sure if we do have any question, but if you do, you can easily open your mic and then you ask. And then if we can look at another problem now, let's see if we can look at another problem. Another problem that we can look at would be, let me see. Yeah, will be this one. Now, when we look at this problem, we're given y to the 2 over 3 times, which is equal to these 3 functions over these 2 functions. So if we check, the top functions are multiplied and also bottom functions are multiplied, and there's a division in between them. It means that for us to simplify this, we can introduce ln, so that we can apply the property that says ln of a over b is equal to ln of a minus ln of b. Then after this, we can now apply the property that says ln of a plus b is equal to ln of a plus ln of b. Now, if we check, this is what exactly happened here. We introduce ln both sides. After that, now we apply the property of saying ln of this minus ln of the denominator, which is what exactly happened. So we say here ln of the numerator minus ln of the denominator. Obviously, ourselves, we are going to write that step. We're going to say ln of x squared plus 1 to the 4 and 3x minus 1 to the 1 over 4, and then x to the 3 minus 2x to the 6. We see that, and then we subtract ln of this denominator. And if we check, ln of this will be, if we apply the property of adding, we're going to say ln of this first function, which will be this, which will be having exponent 4 before we drop it, right? Plus ln of this, which will have to the exponent 1 over 4 before we drop it. And again, we have ln of this, you say, right, before we can drop the 6. Then using that property, what we are saying, this will be ln of x2 plus 1 to the 4 plus ln of 3x minus 1 to the 1 over 4 plus ln of x to the 3 minus 2x to the 6. So we need to apply all these steps before we can drop and so on. So here they were just trying to simplify. After that, we apply the property of dropping the 4 we drop this, the 1 over 4, we drop the 6. So we're going to do the same for these ones. So I think if we have this theory, we can now be able to do questions based on the tutorials and also on the question papers, right? So for an example, for this question, let me check if we have a similar question that I can explain. For example, on this question that we have here, number 3, here they say that y is equals to x, so the sine x. So we see that the function on top is sine x, and for us to easily drop it, we can introduce ln both sides. We see, right? So we just introduce ln, so that we drop the sine x. Now after doing that, we can now introduce the derivative on both sides. When we introduce the derivative, we are going to say, let me write it here, we're going to say the derivative of ln y will be equals to the derivative of sine x ln x. Now this side, we're just going to get 1 over y times dy over dx, and this side we must use now product rule. I'm sure we know product rule, that whenever given two functions with a variable of interest, which our variable of interest is x, so they both contain x, so it means that we must use product rule. With product rule, we're going to say, I'm going to say, let's say I keep sine x first, then I derive ln x, plus now I keep ln x, and then I derive sine x. Let's check. If I derive ln x, I'm going to get 1 over x while I'm keeping my sine x. Is that right? Then I add, now I derive sine x, I get cos x while I'm keeping my ln x, which this will be the case. And then we just simplify them to say, I can just take this sign, put it on top, and then this will be the case. And then I multiply both sides by y to find dy over dx, which is what they did here. So it's just, we are applying the same procedure for all. So if we check, multiply by y both sides, so this 1 over y goes, and then we know what this y is. Y is x to the sine x, so we can just direct substitute that. Then this will be the final product. Now, given that, we can now try to solve any of these problems. But first, I think what we can do, let me do this. I think we can try to check some question maybe on the test 4. Let me see if I can look at some question on test 4 that involves this. Let me see. Yeah, we can check 2.1, right? 2.1 says we're given y is equals to, this is x squared minus 1 over x squared plus 1 to the minus 7 over 17, right? So when we check this, we see that it's a bit complex. For us to derive this, we're going to use chain rule, but we are trying to avoid that. It means that we would what? Would introduce ln both sides. You introduce ln, so you have x squared minus 1 over x squared plus 1, and then we put that exponent. Then now we can drop the exponent. We have ln of x squared minus 1 over x squared plus 1. This is ln y. Then this will be negative 17 over 7. When we apply the ln inside here, we can see that this will just be ln of x squared minus 1 minus ln of x squared plus 1. We say that though if we look at this question, right, we're not told to use logarithmic differentiation, so it's much preferred that you use it if you're told to. But if not, you can use chain rule, so it's better to know both of them, right? So in this case, we see that this will just be negative 17 over 17 ln of x squared minus 1 plus 7 over 17 ln of x squared plus 1. So now I can introduce the derivative both sides. So I just introduce, let me see if I can, let me do this, if I can introduce that both sides. Let me see, we're somewhere here, so I'll just continue from where we are, right? We were somewhere here to say that ln y is equals to negative 7 over 17 ln of x squared minus 1 plus 7 over 17 ln of x squared plus 1. So we're somewhere here. So now I can introduce the derivative both sides, right? So if I introduce the derivative both sides, this will just be 1 over y times dy over dx, which this will be equal to, when I derive this, negative 7 over 17 is a constant, so I'm just going to keep it. Then when I derive this one of ln of x squared over 1, this will just be x squared minus 1 times the derivative of the inside, which will be 2x, right? Then this will just be plus 7 over 17 times, this will just be 1 over x squared plus 1. And the derivative of this inside is 2x. This is just going to be 2x also. So this will be 7 over 17, or this will just be negative 14x over 17 x squared minus 1 plus 14x over 17 x squared minus 1. So this will just be dy over dx. Then we multiply both sides by y, and this will be, we know what our y is, right? So the y would be x squared minus 1 over x squared plus 1. Then we keep the negative 17 over with the negative 7 over 17. So even though on this question we're not going to use logarithmic functions, but we can see if we were told to use it in this question, we're going to use it like this. All right. Then again, if we look at the question below, I think there's a question here where they said use logarithmic functions. So if we look at the question below, we're given a question similar to what we're doing. They say find dy over dx if y is equal to 2 to the sec x. All right. So first thing what we can do here, we can just introduce the ln both sides. We introduce the ln. So if you have any question, you can just let me know. You send it in the group and then you let me know so I can check it. So after introducing this, we can now drop the sec. You see right now, then we have ln 2, which this will be ln y. Then I just introduce d over dx both sides. This will be ln of sec x ln 2. And this is like 5 marks, so those are like 3 marks. But if we check this, we have this side, this usually it's always the case. This will just be 1 over y times dy over dx. And this here will be, I'll keep out the ln 2 because it's a constant. You see, and derive the sec x. And we know that the derivative of sec x will just be sec x tan x. We say right. Then we multiply both sides by y, and we know that our y is 2 to the sec x, and that will be the solution. So when we check this, it was simple for us to arrive there to the solution, as the steps are the same for all the logarithmic differentiation. You apply a law, it's like first thing you introduce ln, you apply a law, then you introduce the derivative, then you derive. After deriving and simplifying, you multiply both sides by y, then you plug your y. You see, right? The same question for all. Now we can go back to the tutorial, since here I think this is the only question where they wanted us to use logarithmic differentiation. So, but another thing before we can go back to logarithmic differentiation, there's a question that I'm interested in here. If we look at this question, we are given, they say y is equals to log 2 7x. The question is, how do we find the derivative of this question, right? So what we can do here, we can say this. We can say that if I introduce the derivative, I think it was how many marks? 4. If I introduce the derivative both sides, this will just be d over dx of log 2 7x. This side I'm just going to get dy over dx. This side I'm going to get, remember this, I want you to remember this, the derivative of this function, log something times this. You see, it's like log something base that. So if it's like this, let me write it here, let me write this property. If we're having the derivative of log bx, this will always be, this is just going to be 1 over ln of b times x times this inside, then times the derivative of that inside. You see right now? So in this case, this will be 1 over ln 2 times 7x times the derivative of 7x, and this will be 1 over ln 2 7x times 7. We see right, then the 7 will cancel the 7. We have 1 over ln 2x. We put the x here. Then that will be the solution for that question. So I'm sure we see what the question is about. Then for this, it will also be simple. If I'm going to derive y both sides, I'm going to derive y and then I derive ln on the other side. I'm going to get dy over dx. And then I get 1 over sine x sine 2x. Remember, when I derive ln of something, I get 1 over that something times the derivative of the inside, which this will be sine x sine 2x. So I believe that this question paper, they were just giving away free marks. So I think it was out of 50, they were just giving away free marks. So if we check this, here I'm going to use product rule. Remember with product rule, so I can just divide this on top. First I start to keep sine x, and then derive sine 2x, plus now I keep sine 2x, and then derive sine x. We say that which this will be all over sine x sine 2x, and this will be equal to, when I derive sine 2x, remember I'm going to get 2 cos 2x, because here I derived the sine, I got the cos, then I derived the inside, I got 2. You see right? Then this is times sine x times this sine x, and then plus, when I derive sine x, I'm going to get cos x, so this is just going to be sine 2x cos x all over sin x sin 2x. And this will be the case. If I wanted, could even simplify further and say that this will be 2 cos 2x sin x all over sin x sin 2x plus sin 2x cos x all over sin x sin 2x. Then when we check the sin x, these sides are going to cancel. We're going to be left with 2 cos 2x over sin 2x plus this side, the sin 2x will cancel. We'll be left with cos x over sin x. And this is just the same as 2 cot 2x plus cot x. So you could even simplify it further if you wanted, right? Then you just simplify it further to that step. It was like 5 marks, so it was worth it simplifying. So if we check this is like 6 marks, so we needed to use chain rule. But let me show you how to use chain rule. I think I'm also interested in this. Then we can go back to those tutorials. And then when we check this one, let me erase here. The question is, how do we find the derivative of a chain rule? So this one, when I'm going to derive it, I'm just going to find, let's say if I introduce d over dx both sides, let me just introduce it here. This will just be x squared minus 1 over x squared plus 1 to the minus 7 over 17. When I do this, I'm just going to drop the exponent first. I apply power rule. Power rule says that I'm going to just multiply here by that exponent. Then I keep the inside. The inside is x squared minus 1 over x squared plus 1. Right? Then I subtract 1 on the exponent. Just that I don't have a calculator here. You can try to subtract and see what you get. So after that, I multiply by the derivative of the inside. Though there's a simpler way to approach this, I'm also going to show you the simpler way of this. So this will just be minus 7 over 17 x squared minus 1 over x squared plus 1 minus 7 over 17 minus 1. So you can just try to find what that is. When we check this, we must use quotient rule. Right? With quotient rule, we are saying that quotient rule tells us that we must first keep the denominator here, then we derive the numerator. Then we subtract. Now we do the opposite. You see right now. It's like that. Then we divide by the denominator and square it. Shall we say this? So this is just going to be the derivative of x squared minus 1. This is just going to be 2x times x squared plus 1 minus the derivative of x squared plus 1 is also going to be 2x times x squared minus 1 all over x squared plus 1 all squared. Alright, then when we simplify this, it's just going to be 2x to the 3 plus 2x minus 2x to the 3 plus 2x all over x squared plus 1 all squared. Then this will be the 2x to the 3 will cancel out, and then we'll be left with 4x over x squared plus 1 squared. Then we multiply by this, then we simplify. You see right now. So that is as simple as that. Then another way to make it simple and accumulate those 3 marks, what you can just do, Look at the question. The question is saying when you're driving here, what you can do, you just let this be g. You say that, or you let that be some function. You can do that. Let's say you let u be equals to x squared minus 1 over x squared plus 1. Then you just derive this. You say right now, you just derive this both sides. You just derive. When you derive this, you see what you get. Then after that, you come back to plug it here. Sure, we see that. So that will be the case. But then this one is much preferred than letting the function inside be something. So since now we know how to do these questions, right, we can, let me see, I think we can now go back to the tutorial and look at some of the questions. And then let me see, we can go back to the tutorial. So on the tutorial we have this. Number one, they say, I think we can look at this C. They say find f prime of x for the following using logarithmic differentiation. If we have f of x equals to x root of x, they want us to use logarithmic differentiation. What we're going to do, we're going to introduce ln both sides. All right. This will be x to the root of x. Then I drop this. Then I just introduce d over dx both sides. Then when I derive this, according to the property of this function, when we're deriving ln of something, we say 1 over that something times the derivative of that something. So the derivative of f of x is f prime. This will be equals to, when I derive this, we realize that this is a product rule. So we're going to keep one, derive the other. So we keep x, we derive ln x, plus we keep ln x, we derive root of x, which is 1x to the 1 over 2. So this will be root of x over x, plus this will be 1 over 2 x to the 1 over 2 to the minus 1 over 2 times ln x. So here just use power rule. Just drop 1 over 2 and then I subtract 1 and get that. Then if we check this, I can now multiply both sides by f of x. So we can have this ln x over 2 root of x. And then that was x to the root of x. If I multiply both sides by f of x, and we know that this is equal to f of x, then this will be the solution. Then if we check, this was simple. We have done an example based on this. And based on this, we can also see that for us to solve such a question, we'll just easily say, let me just introduce ln both sides. Where this will be ln of a to the x3, x to the x2. And then this will just be, in this case, this will just be ln of a to the x3 plus ln of x to the x2. We say right, and this will be x to the 3 ln of a, and ln of a is 1, so I don't have to write it, plus ln of x to the x2. Maybe like this one, I can also drop the x squared. I don't have to go through the long road. I can just drop the x squared and have ln of x. Then when I introduce the derivative both sides, let me not write that because of space. When I introduce the derivative both sides, we say right, deriving a ln of f of x, this will be 1 over f of x times f prime of x, which will be equal, so if I derive this, I'm going to get 3x squared plus, then I keep one and derive the other here, so I'm just going to keep x squared and derive ln x, I get 1 over x plus, then I keep ln x and derive x squared, and we're just going to get 2x ln x. And then this would be, I multiply both sides by f of x. We'll have 3x squared plus x plus 2x ln x. And then if I multiply both sides, it will be e to the x3 x to the x squared. Then this will be the final solution. If you can check, they're all simple, same syntax. You just have to apply the same thing. The structure is the same. You always introduce ln, then you introduce derivative, then you multiply both sides by f of x. Now when you look at number 2, on number 2 they say we're given, if we look at, I think we can start with, on this one we can start with b. If we look at b, we're given y is equals to x squared plus 1 over x plus 1 to the 1 over 2. If I introduce ln both sides, x squared plus 1 over x plus 1, 1 over 2, then I can just drop the 1 over 2. You can see that some things are repeating. We know now that if I want to compute this ln of the numerator over denominator, I'm just gonna say ln of the numerator minus ln of the denominator, just like that. And then I introduce the derivative. So with the derivative, I believe that we can easily derive this. You're just gonna say 1 over x squared plus 1 times the derivative of the inside, which will give us 2x. The same thing here, we do apply the same syntax. So introducing ln would just to be simplifying, or just to use it to simplify the equation that we're given. So this should be the simplest topic to do. So I think that as I checked, let me check again, as I checked, people say that this was the most difficult question they were facing. So I believe that this will not be the most difficult question you are facing so far. It means that when we have a session again, we're going to cover the derivatives of special functions, because I've already sent you the one of L'Hopital rules. But if you have any question based on that, you can ask. Then another thing about implicit differentiation, I think I saw a question here based on implicit on the question paper. I think we can try to attempt it and see how can we solve it. So the question here, they say find d squared y over dx squared if we're given this function. Alright, so what we can do first, we introduce d over dx both sides. Then we have xy minus x squared, which is equal to 9. If we check here, the derivative of y squared will just be 2y times dy over dx, plus when we derive this, then this will just be, the derivative of x squared will just be 2x, and the derivative of 9 will just be 0. Now remember with this theory, right? Remember, if I'm deriving x, let's say, I'm deriving x. What I'm saying is that when I derive x, I get 1. But this is read like this. I'm deriving x. The variable that I'm deriving here is x with respect to x. You see, right? And this gives us 1 times 1 is 1. That's why the derivative of x will get 1. The same thing, if I was to derive x squared, I'd get 2x, but I'm deriving x with respect to x. You see, this one automatically would give us 2x. But now it's a different story when I'm deriving y. When I derive y, I get 1, but I'm deriving y with respect to x. So that's where the implicit differentiation comes in. If I'm deriving w, what this says is that, let's say w cubed, I'm going to get 3 w squared, but I'm deriving w with respect to x. So these two won't cancel out. These won't cancel out. It's only these that cancel out. That's why there's no need for us to write them. So these have been there all along, but there was no need for us to write them. So now, since we are deriving y with respect to x, there will be a need to write them. So now if you continue with this question, we see now why when we're deriving y squared, we wrote 2y dy over dx. And this will be 2y dy over dx plus, when I derive this with product rule, I'm going to keep one, derive the other. So I'm going to keep y, then I derive x here. So I'll show these steps. Plus now I keep x and derive y. And then this negative 2x, I can just take it to the other side to become positive, as long as it doesn't have dy over dx. Then this will be 2y dy over dx plus y. Remember, this is 1 times dx over dx, and there's no need for us to write dx over dx because it's 1. Plus, this will be x dy over dx, which is equal to 2x. So here, I can factor out the ones that have dy over dx. Then the one which does not, I take it to the other side. So this will be 2y plus x, which is equal to 2x minus y. It means that dy over dx will be equal to 2x minus y over 2y plus x. So this is our dy over dx. But then we are asked to find d squared y over dx squared. So what we are going to do now, we're just going to come to this question, the final solution. We introduce both sides, d over dx. We introduce both sides, d over dx. So when I multiply here, I'm going to get d squared y times over dx squared. So this is just going to be d squared y over dx squared, which this will be equal to, now remember this side, I'm deriving this with a quotient rule. So I'm going to first keep the denominator and derive the numerator. So this is just going to be 2, is it 2x plus y? Yes, 2y plus x. And then I derive the numerator, which the numerator is 2x minus y. Then I subtract, now I do the opposite. I keep the numerator and derive the denominator, which is 2y plus x. Like that. Then I divide by the denominator and then I square it. And this will just be 2y plus x. When I derive 2x, I'm going to get 2. When I derive a y, I'm going to get dy over dx minus 2x minus y. Then when I derive 2y, I'm going to get dy over dx. When I derive x, I'm going to get 1, which this will still be over 2y plus x squared. Now, from here, we can now do two things. We can either multiply through, or we substitute our, from here, we direct substitute our dy over dx. But looking at this situation, I think it's best that we start by multiplying through, right? So if I multiply through this will just be 4y plus, instead of 4y, let me just keep it like this. It's fine. I'll keep it the 2 outside. 2y plus x minus 2y plus x dy over dx minus 2x minus y dy over dx minus 2x minus y, and then all over 2y plus x squared. So from here now we can direct substitute our dy over dx, and remember dy over dx is 2x minus y over, so I'm going to direct substitute that. That's just going to be 2x minus y over 2y plus x. So this is going to cancel out, minus this is 2x minus y, then I direct substitute this is 2x minus y over 2y plus x, and then I just subtract this. And then these two won't cancel out, they'll just multiply through, right? So I can just try to expand it from this side, then we'll see where we're going to get to. So let's try to expand it from this side. So when I try to expand it from this side, this is just going to be 2, and this is 2y plus x, then this will be minus 2x minus y. And then we have, let me see what we're left with this side. This will become squared. This will just be minus 2x minus y squared all over, and then this is 2x into 2y plus x, and then we now divide by, the denominator was 2y plus x squared, and then this will be the case. Alright, going further, so let me also put the denominator here. Now from here, after direct substituting your dy over dx, obviously there's some things which will cancel out and some things will multiply through, right? After this case, we can now come and say I'm having something that is acting as both the numerator and denominator. This is always the case. There will always be something that acts as both the numerator and the denominator. So we must eliminate that thing. So the only way to eliminate it is if I come and multiply by it on the numerator and also on the denominator. You see, right? Then this thing will cancel out here. And then here it will multiply through. So this will just be 2y plus x squared. If I multiply it with the same thing, it will square, minus 2x minus y 2y plus x, minus this will cancel out. This will just be 2x minus y squared, which this will be all over 2y plus x. If this multiplies with this, it will be cubed. We say, right? Then from here you can just try to simplify this. Now I'm sure that you will see that it's not as difficult as it seemed. Alright, so you can now try to simplify that. So I think you can try to do this, and then I'll be available for consultations. If you want to consult, you just ask the question in the group or you ask privately. So I think another thing, there was a question that was asked, right, in the group, where I even said, I think I sent a link, right, to say that you can look at the L'Hopital rule there. But this question is simple, right, to a point that if I want to solve this question, remember, if I say this is the limit, let me use a different color. If I say this is the limit as x approaches 0 of 1 over sin squared x minus 1 over x squared. If I direct substitute here, I want us to check the form. The form of this question is, if I direct substitute here, I'm getting infinity minus infinity. The moment you get a form like this, remember here you're only supposed to get two forms, this one or this one. That's when you can apply a L'Hopital rule. But the moment you get a different form, you should start by simplifying that question. So the moment you get a form like this, I must start by simplifying this. So when I simplify this in this case, I'm going to have the limit as x approaches 0. I multiply this like this. You see right now? Then this will be x squared minus sin squared x over x squared sin squared x. Now let's try to direct substitute now and check the form and see if it's still in that form or in a L'Hopital rule form. When I direct substitute on the numerator, I'm going to get 0. I direct substitute on the denominator, I'm going to get 0. Now we see that this is in a L'Hopital rule form. So for that, I'm going now to say, before I do anything, when you see that this thing is in a L'Hopital rule form, you must introduce d over dx on the numerator and denominator. You see right now, I introduce d over dx on the numerator and denominator. So when I derive the numerator, I'm getting, so let me write the limit, I'm getting 2x minus, this will be 2 sin x cos x, alright, all over. Remember, when you derive sin squared x, when you derive, let me remind you this, when you derive sin squared x, this is the same thing as deriving sin x or squared. You first drop the 2 according to chain rule, you to power rule, you drop the 2, you keep the sign, you subtract 1 here so it remains like this, then you multiply by the derivative of the inside, which the inside there is sin x. Then when you derive this, you'll get cos x. That's why I'm having minus 2 sin x cos x. So that will be the case for this problem, right? Then when I try to derive the denominator, if we look at the denominator here, this is a product rule. I'm going to apply product rule for me to derive that. And with product rule, for me to derive that, I'm going to keep one, derive the other, plus and so on, right? So this will just be, let me do this, just be all over. When I derive this, I can drive this aside. I can say, let's say I start by keeping sin squared x, and then I derive x squared, I'm going to get 2x, and then plus, now I keep the x squared, I derive the sin squared x, this will just be 2 sin x cos x. I'm sure we say this. So when I check this direct substitute again, I want to check if this is still in L'Hopital rule or not. When I direct substitute here, this will be 0. I direct substitute here, this will be 0. Right. And then with this one, if I direct substitute, it will also be 0. But for that, we can try to simplify this before we continue driving. Right? To simplify this is the same thing as sine 2x, right? And also to simplify this is the same thing as sine 2x. So here I would try to simplify like this. So let me try to write it down here from where we left it, and then we see how can we proceed from there. Since the space no longer fits there, just going to add the page. So there we had the limit as n as x is what it's approaching what there, x approaching 0, x approaches 0 of this is 2x minus, that was 2 sine x cos x, so that I said that we can change it to sine 2x all over the denominator was this is 2x sine squared x plus 2x squared. So let me just copy this. It's 2x sine squared x plus this is x squared sine 2x. Right, I think that is the case. When we change sine 2 sine x cos x, we're gonna get sine 2x. Now we check the form again. Remember, we just simplified it, we changed to this, we check the form if it's still in L'Hopital rule or not. When I substitute on the numerator, I get 0, denominator also gets 0 here. So it's still in L'Hopital rule form. So I can now continue introducing the derivative again. D over the x of the numerator all over, and introduce it again on the denominator. Like this. Then when I derive this, on the numerator I'm going to have 2 minus 2 cos of 2x all over. When I derive the denominator, this is product rule, right? That's part. So I'm going to keep, let's say, I keep 2x first. Then I derive this sine squared x. I'm going to get times 2 sine x cos x plus, now I keep the sine squared x. I derive the 2x, I get 2. Alright, times 2 plus, when I derive this, I keep the x squared first, I derive the sine 2, I get 2 cos 2x plus, now I keep the sine 2x, I derive the x squared, I get the 2x sine 2x. Alright, now if we check this, let's see what we get. Now I can also change this again. This will be sine 2x. Let's see what I get when I try to plug. Let me just check. If I plug 0 here on the numerator, I'm going to get what? I'm going to get 2 minus here. What am I going to get? I'm going to get 2 again. So this will be 0. So 0 minus 0 is 0. On the denominator, let's see, when I plug here, I get 0. I get 0 again here. I get 0. I get 0. So this is still in the form of 0 over 0. So we can still introduce, you see, right, we can still, maybe before we, let's introduce this and then we simplify it. Minus 2 cos of 2x all over. I introduce the derivative here, but I'll be simplifying it so simple to keep it short. This is 4 not 4, this will be 2. When I'll have 2x, then this one I can simplify it, 2 sine 2x, right, plus this will be 2 sine squared x, plus this will be 2 x squared cos 2x, plus this will be 2 x sine 2x. If we check these two are the same, right, I can also try to simplify that. That will just be 4. I say that they're being simplified, right? That will just be 4x sine 2x. So since that is the case, I can still continue to say when I derive the numerator, I'm going to get minus 4. This will become positive, so it's like this. Let me just derive it step by step. When I derive the 2, I'm going to get 0 minus 2. When I derive the cos, I'm going to get minus sine 2x. When I derive the 2x, I'm going to get 2. So this will just be 4 sine 2x. You see right now. So here I'll just be having 4 sine 2x. So this will be all over. When I derive this, we see that I can keep one, derive the other, right? Let's say I keep 4x, I derive sine 2x. I'm going to get, this will be 2 cos 2x. We say right, plus, and then now I keep this 4x, just gonna get 4. We say right, and then with this, I'm going to get plus 4. When I drop the 2 times will give us that sine x cos x. So this one I don't even need to keep it as 4, I can just keep it as 2 times 2. We say right. Then when I derive this is gonna be similar. Just going to say plus, I keep 2 x squared and derive cos 2x. That will be minus, or maybe let me just start by keeping derive the x squared. This will just be 2x. Then now I keep the x squared and keep the 2x squared and derive the cos 2. Then with the cos 2, I'm going to get negative sine x. So let me write it here. Sine 2x. We see right. So this, we could drive it like this, right? Then if we check this, we can try to check what is going to happen if I plug. Let's see here. If I plug here, I'm going to get, we know that the x will give us 0. If I plug here, I'm going to get also 0. If I plug here, I'm going to get 0. If I plug here, I'm going to get 0. I plug here, get 0. And then I plug here, get 0. So this will still be 0 over 0, right? So this will depend on how do you simplify it. So if I keep on, I think the last derivative will be, the other derivative will be the last one. Because when I derive the numerator, let's say I was to derive this one, I'm going to get 8 cos 2x. I'll not get 0 anymore here. You see right? So this will be the last derivative. You see right? And when I derive this one on the denominator, so I want to show you this. When I derive this, right, this will be a product rule. It's gonna give me something that when I plug at the end, it will be 0. But when I derive this would give me 8 cos of 2x plus the derivative of this would be, let me write this so that you can see. The derivative of this would be, if I derive this one will be 8. Let me just keep the 8. If I derive x, I'm going to keep this one 2x. Even this one won't give me 0 anymore. You see right now? Plus, now I keep the 4x and derive, not 4x, I keep the 8x and derive the cos 2. That will be negative 2 sine x. So this one will give us 0, you see, right? But this one give us 0, this one give us 0. Plus, if I derive this one I can change it to 2 sine 2x. If I derive that will just be minus, it will just be plus 4 cos 2x. Then if I derive this, I would use again product rule. I derive this, I use again product rule, right? But if we check, we won't be getting 0 over 0 anymore. I can still be able to plug here. I get 8. When I plug here, I get 8 plus 8 plus 4. And then you can check what else are you going to get from these other ones. You see that? But if I can tell, this one will still give us 0 if we continue driving. And then this one, if I continue driving, it won't give us 0. We can get something like, let's say if I keep this one, 2 cos 2x, and I drive 2x, I'm going to get 2. So this will be 4 cos 2x. So this one will give us 4, 4, 4, 4. Then you could continue and check in that, right? Then you'll see what the solution is at the end. So it will be 8 over something, which would give us a fraction. So without any waste of time, I think we can stop. You can look at the other videos which I sent for elementary. But I'm going to include this here really interested in us. Then from there you take it from there. Then you can also try to do this basic and see if you can find a simpler maybe try to simplify it and then if it is more simpler you get to the solution fast. But at the end you're gonna get to the solution. So yeah, I think this will be the end of today's session. We can proceed from here tomorrow. I think we'll discuss which topic are we supposed to do and which question paper we're supposed to look at.